Problem 73 on the homework was the problem of the fish on the spring. We hang a fish, or we attach a fish to an initially unstretched spring, and then we release it. So the fish will descend down to some position and it'll come back up. The original position we're going to take to be y equals 0. That's the original position. The spring is unstretched. Now, I'll leave it to you to interpret the word unstretched as applying to the spring as opposed to the fish. Okay, so the fish then descends. When it's at position y, where this is y equals 0, and we're going to assume the positive direction to be up. Okay, so when the fish is at position y, and y will be a negative position, what's its potential energy going to be? Well, its potential energy is going to be its weight times y plus 1/2. Well, okay. Gravitational potential energy is going to be its weight times y. Now, y being negative as the fish descends, that is going to be negative in connection with our definition of potential energy. That's going to be equal and opposite to the work done by gravity on the fish, because gravity's down, the fish is moving down. Gravity is going to do, the fish has moved down by the time it's in position y. So gravity will have done positive work on the fish. But y being negative, well, the potential energy change will therefore be equal and opposite to the work done by gravity. It'll be negative, and the weight times y is going to be negative because y is negative. And this isn't positive. I guess I better clarify this, even if it gets a little sloppy. That's position y, not positive y. Okay? So the weight times y is going to be negative as long as the fish is below the equilibrium point. And the potential energy of the spring is clearly 1/2 ky squared, so that the total potential energy is mgy plus 1/2 ky squared. And this is all measured relative to y equals 0, which is the initial unstretched position of the spring. So, another thing is delta WNC is 0. We're assuming there's no dissipative force, no friction, no air resistance, etc. And that's pretty much going to be true if you got a well-oiled spring. Of course, the spring has to be light, or the spring itself, in extending, is going to lower its center of mass, and there's going to be a change in its potential energy. In any case, it follows that the change in the kinetic energy as a function of y is equal and opposite to the change of potential energy as a function of y. That because since delta WNC is 0, no work done by non-conservative forces, whether on or by, it's equal to 0 either way, tells us that delta KE plus delta PE equals 0 by the general work energy relationship. So we determined that delta KE and delta PE are equal but opposite in sign. Expressing delta KE as a function of y, delta PE as a function of y, we see that delta KE at position y will be equal to the negative of the delta PE, which is negative mgy minus 1/2 ky squared. And the kinetic energy, of course, started at 0. So the change in kinetic energy is just equal to 1/2 mv squared, where v is also a function of y. I could have written that as 1/2 m v of y squared. Trying to be economical with space, but clarification that this does mean 1/2 m times the value of the velocity function v of y squared. Okay, so what do we end up with? We end up with, well, the change in kinetic energy is just equal to 1/2 mv squared. So 1/2 mv squared, change in kinetic energy as a function of y, is going to be equal to the negative of the potential energy, which is the negative of this, which is this, the negative of this, which is equal to this. So we have this equation for the velocity. We solve for the velocity, and it's a very simple solution. We get velocity is plus or minus the square root of negative 2 mgy minus ky squared. Now at this point, you see, that looks like you're taking the square root of a negative. Well, what's the caveat here? There's no guarantee that y is positive, and in fact, if the positive direction is this way, the position y will be negative relative to the initial position at any of the points that we're considering. So, since y is negative, negative 2mgy is positive, so that this expression can be positive as long as 2mgy has a magnitude that's greater than that of ky squared. So, when does the maximum velocity occur? Well, when people solved this, I think people uniformly said, well, the maximum velocity occurs when dv dy is 0. Okay, that's, this velocity is a function of y. It's going to be maximized or minimized when the derivative with respect to y of the velocity is 0. The derivative of velocity with respect to y is dv dy. That will equal 0. We might want to do a second derivative test or a first derivative test to determine whether this is a max or a min, but it's pretty clear from the context that it's going to be a max. That's always good to verify that, and I recommend that you do, but I'm not going to do it here. Okay, so the maximum velocity occurs when this is the case. If you take the derivative of this function and set it equal to 0, you're going to find, I believe, that that occurs at the point that's halfway to the point where you get the maximum drop. Maximum drop occurs when 1/2 mv squared equals 0. That implies that v equals 0, which implies that the expression under the radical will be 0, so that negative 2mgy minus 1/2 ky squared would equal 0. And we can easily solve that. We factor out y, we get y times 1/2 k. I'm going to factor out the y, and I'm also going to multiply this by a negative, so I don't have to worry about negative signs. This is equal to 0, so multiplying both sides by negative, we're still going to get equality with 0. So we get this plus 2mg, and I left my y off of this because I digressed there. Okay, we get y times 1/2 ky plus 2mg equals 0. The solutions, y equals 0 or 1/2 ky plus 2mg equals 0, so that y equals negative 2mg over k. And that gives us a negative value of y. Not sure that the camera's gone low enough to see that. Okay? So when y equals negative 2mg over k, the fish will come to rest. If you solve this equation, I believe you're going to get y equals negative mg over k. The fish reaches its maximum velocity at the halfway point, although you should work that out and verify that. But I think most people got that in their solution. Okay, again, I've used a symbolic solution here. And that goes with the admonition to use symbolic solutions, but also do dimensional analysis. What are the dimensions of mg over k? That's kilograms times meters per second squared. K is newtons over meters. So that's going to give you kilogram. Well, let's do it. Let's write it out. Okay. The units of this, using SI units, the units are going to be kilograms times meters over second squared, kilograms, divided by K, which is newtons per meter. That equals kilogram meters squared per second, divided by newtons, and newtons are kilogram meters per second. Make sure that camera's all the way down there so we can see what I'm writing. Don't have a lot of room here. And everything here divides out except the meters. So we do get units of meters. The dimensions work And there are all kinds of interpretations you can make to these various quantities, but that's sufficient to illustrate the solution of the problem. I can't help but add another interpretation, another fact for this motion because it's so relevant to simple harmonic motion, which is going to tend to give people some trouble. Okay? The maximum displacement is negative 2 mg over k. Maximum velocity, if you solve these equations, is going to be at negative mg over k, halfway to this maximum displacement where the fish comes to rest. That's the point of maximum velocity, the halfway point. So the fish descends, speeding up, then it slows down, then it'll come back and it'll keep oscillating, assuming delta W non-conservative to be 0. It'll keep oscillating forever. Now that's the ideal. It's not going to really happen. You should be aware that this maximum velocity coincides with the new equilibrium position of the system. Once you add the fish, the spring is no longer at its original equilibrium position. The equilibrium position of the spring and fish is going to be at this point. That's the point at which the net force on the fish is going to be 0. So F net equals 0 at this position. And when F net equals 0, that's when the fish has reached its maximum velocity. That's the point also at which the net force on the fish goes from being downward, gravity exceeding the spring force, to being upward with the spring force exceeding gravity. And that's the center point, the equilibrium position, the new equilibrium position. This position here is the center point for the simple harmonic motion. It's the equilibrium point for the simple harmonic motion of the fish as it oscillates on the spring.